Hey, cool. Cool. So, hey guys, thank you all so much for coming out. This is super exciting to be at the first PyCon Canada that's outside of Toronto and has largely been organized by a non-Toronto team. So this is super cool. To give you just a little bit of background on myself, my name is David Wolever. I tweet a lot at Wolever. I'm co-founder of a company called Akindi. We do Scantron, you know, like Scantron multiple choice bubble sheets. So we do those, but less terrible. And the other important thing that you need to know about me for this talk is I have a really irrational love for SQL. It is problematic. So the thing that we're going to be talking about here is Countstar. So Countstar is the function that counts the number of rows. So for example, if we wanted to count the number of attendees that are at PyCon this year, we could use select Countstar from attendees, and we might get something that looks like this. And one day at work, I was playing around and I wanted to just count the number of messages that we had in a messages table. So, you know, I type out the query, let it go, and I wait, and I wait. And eventually, we get that result back. And wow, like, that is really slow. Counting the number of rows in a table should be like quick and easy. This is what databases are here for. So what's making it so slow? Now, just before we go any further, I want to have a quick refresher on SQL. So SQL is an initialism as opposed to an acronym that stands for Structured Query Language. It's a declarative language that you use for querying data. So for example, let's say we wanted to find out where all of the PyCons have been in the last few years. We could use SQL. And please forgive how incredibly incomplete that list is. And further, if we wanted to find out just which PyCons had been in Montreal, we could use a query that looks something like this. It can also be used to do aggregate calculations like summing, or in this case, counting. So if we wanted to count the number of PyCons that had been in Montreal, we could use a query like that. And to break that down just a little bit, we have the count star. What that's saying is we want the result that we want to get is a count. And if you're wondering about that little star, what that's there so that we want, that's there because we want to count all the rows, not just the rows with non-null values. And if that doesn't make any sense, don't worry about it. You can ignore it. So that covers the querying part of SQL. And I'm sure for some of you, this is old hat and you're getting a bit bored, but don't worry, give me like 4 minutes and we're going to be getting into new interesting stuff. For the moment though, I want to take a second and look into that second part of the definition, the declarative part. And just a warning, if there are any language lawyers out there, I'm going to be using some generalizations. The things that I'm going to be saying are not 100% true, but they're going to be true enough for now. So, declarative languages. In a declarative language like SQL, you describe what you want. Contrast that with an imperative language like, for instance, Python, where you're going to be describing a series of steps that will, hopefully at the end of the day, get you to what you want. So, for example, if you're hungry in a declarative language, you might say, hey, I want a lettuce and tomato sandwich. Whereas in an imperative language, you might say something, you might have to say something like, go to the fridge and get a tomato, then go to the knife drawer and get a knife, then cut the knife, use the knife to cut the tomato and put it on bread, and so on and so on and so on. Or possibly for a more concrete example, if we were going to use Python to build that same list of PyCons that have been in Montreal, we might write code that looks something like this. Now, notice that what we're doing is describing a series of steps, a series of operations. We're going to be opening a file, iterating over the lines, splitting each line up on the white space, comparing the city in that line to Montreal, and if the city matches, we're going to print that to the screen. Now, contrast that with SQL, where we're going to be describing what we want. First, we're going to say we want to select star, so that is, give me all of the columns, all of the pieces of data associated with a PyCon. In this case, it's going to be the year, the country, and the city. And from the PyCon's table, so table in SQL parlance is the collection of data. And finally, we want to filter out for only the ones that have been in Montreal. Now, one of the really big advantages of declarative languages like SQL is they can be really powerful. You can have a very small amount of code that gives you, quite powerful, quite meaningful results. After all, you're telling the computer what you want, and the computer's the one that's responsible for going out and figuring out how to get it. But that does come at a cost. See, computers, as you all are programmers, and I'm sure you know, are not the smartest, and they don't necessarily make the best decisions all of the time. In an imperative language, when something comes up and the computer isn't quite doing what we expect, more often than not, it's straightforward to debug and diagnose what's going on. After all, we've written out an explicit series of steps, so we can just step through ourselves and figure out where is that misunderstanding between us and the computer. On the other hand, that's not so true with declarative languages. When a program in a declarative language is misbehaving, so for instance, in this case, that count query taking much longer than we'd expect, we need to understand not just what the program that we wrote is doing, we also have to dig in and understand how the computer is transforming that into the real, actual, concrete steps that are going to be taking place. So, getting back to this question of why is this count so slow? In diagnosing that, the first thing we need to figure out is what's going on under the hood. What are those actual concrete steps that Postgres is taking to count the number of rows in that table? And fortunately, Postgres has a command called explain that we can use to help with that. And I want to be clear here. I'm going to be talking about Postgres specifically, but almost everything I say applies to almost every SQL database. So, the explain command, like the name suggests, is going to explain the steps, ask Postgres to explain the steps that it's going to take in executing that query. Some water. So, to start with a simple example, we're going to look up one message by its ID. I'm sure any of you who work with databases have written a query that looks like this a million times. And what we get is this thing called the query plan. This is the plan that Postgres is going to follow to execute that query. Now, in here, there are a couple important things that we need to notice. So first, this index scan. Fully explaining what an index is a bit out of the scope of this talk, as much as I would love to do that. If you see me afterwards, please feel free to ask and I'll talk your ear off. But for now, I'd really encourage all of you, even if you think you know a bit about indexes and databases, to check out usetheindexloop.com. This site is spectacular, and unless you're an actual full-time professional DBA, I would be astounded if you didn't learn something new from it. Anyway, the important thing that we need to know about indexes for the purpose of this talk is that they're one of the tools that the database uses under the hood to let us quickly access data. So, what that index scan portion is telling us is that we're going to be using an index to do this lookup. The next important thing to notice here is going to be the cost, row count, and width estimates. So these are super cool. Basically, what's happening under the hood is Postgres keeps track of the statistical distribution of all the data that you put into it. So when you give it a query like this, it's not just dumbly saying, oh, okay, well, it looks like I maybe should do this. It's actually going to be taking the parameters that you give it, comparing those to the statistics that it has on the tables, and figuring out what the most efficient, or hopefully most efficient way of accessing that data is going to be. So the first part of that is going to be the cost. The details of the cost are, well, I don't want to say anything, they're fascinating, but we're not going to go over them too much now. Suffice it to say that smaller is better here, and this is a very good cost. The second really cool thing is this row count estimate. So from just the query, before Postgres has done anything, it's got a pretty good idea of approximately how many rows it's going to be returning. Now, again, in this case, because there isn't, and this is for the database geeks out there, because there isn't a unique index on that ID, we're getting a count of 13 rows, so it suspects that about that many rows are going to be returned. And although if there was a unique index, obviously it would be just one. The second part, the width, is the number of bytes per row returned. And internally, Postgres is going to be using all this to figure out what the best way to execute that query is. Anyway, finally, that index condition tells us what we're going to be looking for in the index. In this case, obviously, it's just 1, 2, 3, 4. Now, I find it super fascinating looking at the plans for more complex queries, and I'd really encourage you all to give it a try sometime if you use Postgres or MySQL or any kind of SQL database at work. One of the really cool things you should poke at and try is just changing those parameters. So for instance, in this query plan, if I change that 1, 2, 3, 4 with like 100 billion, the plan changes dramatically, and the results I get would actually be significantly slower. But I'm not allowed to talk for 4 hours, so we need to move on. Anyway, so now that we know just like a tiny little bit about the query planner and that output of explain, we can look at this Countstar query. So we're going to ask for the query plan. Oof, and that sucks. The first thing that we're going to notice is that sequence scan on messages. What that means is Postgres is going to have to go to that messages table and look at every single one of them. There's no shortcuts it can take. The other thing is that row estimate. That tells us that we're going to be getting back about 35 million rows. So no wonder it's so slow. Postgres isn't able to take any shortcuts, and there's no optimization being performed. When I'm asking for a count of the rows in that table, it actually has to go to each one of those 35 million rows and add 1 to a counter. And really, that seems weird. Like, counting the number of rows in a table, that should be probably one of the simplest operations, one of the most common things you want to do. How much data do I have? What is keeping that from being fast? And to be clear, the people who built Postgres are very, very smart. So I'm coming in with a hypothesis that if I can't do it, there must be something of a reason. Oh boy, I forgot to advance my slides. So we're going to do what every good developer does and take a quick trip to Google. And the first result is going to be the Postgres Wiki on slow counting, because this is such a problem that they have a whole wiki page devoted to it. And it's going to give us this monstrously helpful explanation. You see, the reason this is slow is related to the MVCC implementation of Postgres SQL. The fact that multiple transactions can see the different states of data mean that there can be no straightforward way to Countstar to summarize the data across the whole table. Postgres must walk through all rows in some sense. Oh, well, there we go. I think that summarizes it. Not so much. So, to dive a bit deeper and understand what's going on here, the first thing we need to understand is MVCC. So MVCC stands for multi-version concurrency control. And it's the thing that lets you have multiple concurrent readers and writers, that is, multiple different people writing to and reading from the database all at once without everything breaking all of the time. So, cliche warning ahead. This is, if you've done any sort of reading about databases, the most common example. Imagine you are working at a bank and your boss has asked you to write the function that transfers money from one person's account to the other. You would write it and it might look something like, well, I'm sure you guys would do a better job, but one might hypothetically write it like this. And that's pretty straightforward. We're gonna deduct the amount from the source account. We're gonna add that into the deposit to the destination account, and we're going to pretend that everyone has the money and whatnot. And then we're going to save the two accounts, and that's great, right? No. There's a couple problems with this. In fact, there's quite a few problems with that. But the one that I really want to focus on in particular is this one. And it is just a little bit contrived, so please bear with me. What happens if right in the middle of executing that function, right after that first account is saved, but before the second account is saved, the FDIC comes along and asks the bank to account for every dollar in every account? Well, they're going to find that there's $100 that has just vanished. It's been deducted from that first account, but it hasn't yet made it into that second account. And for a slightly less contrived example, if the program was to crash in the middle, then we would also have $100 that has just vanished. And this is the problem that, well, one of the problems that MVCC solves. And in Postgres, the word we use, the implementation of MVCC is with transactions. So transactions are the tool that Postgres uses to take a bunch of queries that all need to happen together and make sure that two things happen. First, that while those queries are being executed, nobody else can see that partial state. So for instance, if I've deducted $100 from one account and haven't yet put it back into another account, anybody else looking at that list of account balances will see the pre-deduction balances. It also makes sure that if the database crashes or the program crashes, we don't end up in an inconsistent state. So the best way to show this off is with every speaker's favorite thing, a live demo. So I'm going to have two connections to Postgres here. Is that all big enough for everyone? Back? No? Okay, tell me when. Okay, good. And first we're going to show select star from accounts. We're going to see we have a very small bank. Oops, sorry. Okay, good. And on this side, this is going to be another connection, so this could be another web request or who knows what. We're going to start that transfer of $100 from one account into the other. So the first thing that we're going to do is use the begin keyword. That tells Postgres that we want to start a transaction. The things that we're going to be doing next should all either happen all at once or not at all, and nobody should be able to see that intermediary state. So first thing is we're going to deduct that $100 from Alex's account. We can see there, they're $100 short, but if we go next door, everything is still nice and consistent. Next thing we're going to do is deposit that $100 into Chris's account. And again, we can see that in this transaction, that transfer has successfully taken place, the balances are correct, but still, nobody else can see until we take the final step and commit. That's our way of saying to Postgres that, cool, we're done, ship it. And now both of those changes at once have been updated and the world can see them. So I don't know about you guys, but holy crap, that is super cool. Wow. And you might be wondering, though, rightfully, what the heck does this have to do with counting? So to understand, we need to go just a little bit deeper and find out how transactions are implemented under the hood. So in other words, how is it that Postgres can have one set of data for this one transaction and a totally different set of data for this other transaction? And of course, I only use one transaction, two transactions in this example, but this works just as well if we had 10, 100, 1,000 transactions, each changing an arbitrarily large number of rows and an arbitrary number of tables. How the heck does that work? So, to understand, the first thing that you need to know is that under the hood in Postgres, when it saves rows to disk, they're totally immutable. Once it's been written, it never changes. They're actually also never removed. So when a row would be updated, so an update statement, for example, instead of changing that row on disk, Postgres actually writes a whole new row. So to make that more concrete, let's take that bank transfer example. At the beginning, we have two rows in the table and the two balances. We have the update statement that comes along to transfer from one account to the other. And the result is writing a whole new row. So now we have 3 rows in that table. Second update, second new row. Now that table has 4 rows. But hold up. If the table actually has 4 rows, why do the queries only give us 2? What's going on there? How does Postgres know that in the one transaction it should show these 2 rows and in the other transaction these 2 rows? Well, this is going to be the final piece of the puzzle, the XID. The XID, or transaction ID in Postgres parlance, is a unique sequential integer that's assigned to each transaction. So for example, if we begin a transaction and ask for the current ID, we get a number. And in the same transaction, if we ask for the ID again, we'll get the same number back. But if we start a new transaction and ask for the ID again, we're going to get a new number. We're going to, in this case, the next number. And just for completeness, even if you're not explicitly inside a transaction, each statement is executed in a transaction, so you will get a unique transaction ID. And whenever a transaction creates, updates, or deletes a row, that transaction ID is going to be included in that row in one of 2 columns. First, there's the xmin column, which is the transaction that row is created in, and the second is the xmax column. That's the transaction that row is deleted in. So notice in this case that the xmax is empty because neither of those rows have been deleted. But let's walk through and see those updates again and see what happens with the xmin and xmax. So first, we're going to issue that update. We're going to transfer $100 out of Alex's account, and you'll see that the new row has the transaction ID 110. So that's the transaction that is doing this update. The second thing that's going to happen is the xmax of the old row is going to be set to the same transaction ID. And so yes, I did lie a little bit. I said that rows were immutable, but actually it's just the data in the rows that are immutable. Postgres does update these bits of metadata from time to time. So same thing happens when we go and issue that next update. We're going to be creating the new row with the xmin of 110 and effectively deleting the old row by setting the xmax. Now, one of the interesting things that I want to make a note of is that when a transaction is committed, when a transaction is committed or aborted, no rows are modified. That commit is an order 1 operation. It's kind of out of scope to explain exactly why now, but it's pretty cool. You can think through it and figure out exactly why that's the case. Anyway, so hopefully by this point, you're starting to get an idea of what's going on and how Postgres is able to figure out which rows are visible to each transaction. And so we're just going to walk through that. When you issue a query and Postgres needs to figure out which rows to return, it runs a straightforward function, something like this. To check to see if a row is visible to the current transaction, we're going to first check to see if the xmin, so that is the transaction that created the row, is greater than the current transaction. If that's the case, that transaction in the future, the row is invisible. Second, we're going to check the row's xmax, so that is the transaction that deleted the row. If it was the current transaction or one in the past, that row has been deleted and it's invisible. And otherwise, it is visible. Now, like I promised, that is a bit of an oversimplification. It's more than good enough to understand what's going on here, but I do want to appease the database geeks in the audience, so I need to be a little bit more precise. What's actually going on is, remember that transactions can be either committed or aborted. And that needs to be considered when we're checking the row visibility. So we don't just check the xmin, we also check to see if that xmin was aborted. Similarly, we don't just check the xmax, we check to make sure that it was actually committed. And that is also a lie because checking the state of a transaction, whether it's committed or aborted, is kind of slow. So Postgres also caches that on the rows themselves. And there's actually, it even goes further, but anyway, it's good enough for now. And also, we finally know enough to answer the question that we came here for. Why the heck is that Countstar so slow? And hopefully you can see it's slow because there is no one count. The number of rows in a particular table depends on the current transaction. And because there can be a whole lot of transactions active at the same time, there's no sensible way that Postgres can cache and calculate that number of rows in an efficient way for every single transaction. So do we still have time? Oh, 5 minutes, perfect. Oof, look at this. So since you all are very smart and have been paying perfect attention, I'm sure there's a few questions that have come up in this, because there are obviously some trade-offs in that implementation. And one of the really obvious questions is going to be, if rows are never deleted or updated, what happens to them? Like, why doesn't the database just grow forever? Theoretically, if we had a table with just one row, where that just one row is being updated, doesn't that mean the table on disk would grow unboundedly? And actually, the answer is yes, except for vacuum. So vacuum is this cool command in Postgres that runs different kinds of routine maintenance. And one of the bits of routine maintenance that it does is it walks through every single row in every single table. So as you can imagine, that takes a while. It's not an easy thing to do. And it removes the rows that it can prove are no longer visible to anyone. So it checks that xmax, and if that xmax is smaller than any active transaction, it actually physically deletes them. Now, an important caveat there is it doesn't actually delete them and give the space back to the operating system. It just deletes them and lets that space be reused by other rows in that table. So it's an important thing to be aware of if you have a really large table that you delete a bunch of rows from because you need to save some disk space. It's not going to work. All right. So the second thing that you might be thinking is, I had mentioned that transaction IDs are these sequential integers. But hopefully whenever you think of sequential integers, one of the things you consider is what happens when that integer overflows. What happens when it goes beyond 4 billion? Well, yeah. One of the other pieces of routine maintenance that vacuum performs is updating internal records of what the minimum and maximum active transaction IDs are, so that it will know if those two get too close together. Because obviously, if the maximum transaction IDs are obviously wrapping around, but if the maximum transaction gets too close to that minimum, you're going to see a message that looks like this. And that comes within about 2 million transactions of the next message, this one. When you have less than 1 million transactions left, the database just locks up. You can't do anything except hopefully clean it up. And if you're curious what that process looks like, our friends over at Sentry have a really good write-up for what happened when it happened to them. Now, the last question you might have in your head is, I mentioned that each row only has one xmin and xmax. Well, so what happens if 2 transactions try and update one row at the same time? And the answer is the second one just always blocks. It's really inconvenient, and there's no way around that. But I would really, again, encourage all of you to play with that and learn about those semantics, because if you're using Postgres as a database, it's incredibly powerful to know how transactions work, and it's also will save you an incredible amount of time debugging if you understand weird edge cases like this one. So, finally, I do need to make the pitch that I'm hiring. I mentioned my company Akindi. We do use Postgres, and we use Postgres with quite a bit of data because we, not to brag too much, but have quite a few customers. We build this product that lets teachers print off multiple choice bubble sheets from any printer, scan them in from any scanner, and get all the results online. That is exactly the way that you think it should work, except we are, and this is not bragging, this is like the objective truth, just about the only ones, and definitely the only ones doing it well in the market right now. So if working on software that makes teachers' lives less terrible is a thing you might enjoy, especially if you're in or around Toronto, I'd love to talk to you. Send me a message, and yeah. Finally, I'm going to be posting these slides to Twitter, where I have references that you can go through and see all the different things. So, thank you all so much for listening.